All right, here we are for day 25, last day in the advent of Code 2020 Code Puzzle Challenge thing. Well, this one was pretty good. A few interesting problems. Definitely learned a few things. Um, and it's always good practice. It's definitely good for learning a new language, or even becoming more familiar in a language. It definitely helps me become more familiar in C Sharp, even though this is probably one of the languages I'm most comfortable in. We're, I guess, making our way to our island. Well, we're on the island, right? So yesterday we goofed around on the hotel floor, rearranging tiles. And the big thing for yesterday is, how do you represent uh, hexagonal coordinates in a useful way? Something that's time efficient to search through, something that's easy to reason through. And luckily, our friend Google and I guess DuckDuckGo, but our friend the search engine and our other friend Wikipedia helped us out. I guess the coordinate system we used was, I think it was called HECS, High Efficiency Hexagonal Efficient Coordinate System. I think that's what it was called. But yeah, I didn't know that, but it made sense once I dove into it. Alright, day 25. You finally reached the check-in desk. Unfortunately, the registration systems are currently offline. The room key is a smaller RFID card. Your room is on the 25th floor and the elevators are temporarily out of service, so it takes a while. It takes a little bit of energy to climb the stairs, navigate the halls. You finally reach the door to your room, swipe your card, and beep. The light turns red. Examining the card more closely, you discover a phone number for tech support. Let's see. You describe the status of the elevator. You need to reverse engineer the cryptographic handshake the card does with the door and inject your own commands into the data stream. Sounds simple. The handshake used by the card in the door involves an operation that transforms a subject number. To transform a subject number, start with the value 1, then the number of times, call the loop size. The loop size. Perform the following steps. Set the value to itself multiplied by the subject number. Set the value to the remainder after dividing the value by 2020 1227. The card always uses a specific secret loop size when it transforms a subject number. The door always uses a different secret loop size. The handshake works like this. The card transforms a subject number of 7 according to the card's secret loop size. The result is called the card's public key. Okay. Is this a prime? The door transforms a subject number of 7 according to the door's secret loop size. The result is called the door's public key. The card's public key, the door's public key. Sounds like how AES works. The card in your door used the wireless RFID symbol to transmit the 2 public keys, your puzzle input, to the other device. Now the card has the door's public key and the door has the card's public key. Okay. The card transformed the subject number of the door's public key according to the card's loop size. The result is the encryption key. And then the door does the same thing, and that's the door transformed the subject number of the card's public key. Result is the same encryption key. You can use the two public keys to determine each device's loop size. You'll have enough information to calculate the secret encryption key that the card and door use to communicate. This would let you send the unlock command directly to the door. For example, suppose you know that the card's public key is this. With little trial and error, you finally work out that the card's loop size must be 8, because transforming the initial subject number of 7 with the loop size of 8 produces the same number. Card's loop size must be 8. Okay. Then suppose you know that the door's public key is this. By the same process, you can determine that the door's loop size is 11, because transforming the initial subject number of 7 with the loop size of 11 produces this. Okay, what does our puzzle input look like? The door and the card, right? Or no, the card and then the door. Let's get the test input. Transforming the subject number, the loop size of 8 produces the encryption key. Transforming the subject number of this with the loop size of 11 produces this encryption key. It produces the same. What is the encryption key the handshake is trying to establish? All right, let's see. Going back. Set the value to itself, multiply by the subject number. Well, let's see. Let's see. It's the card and the door public key. Guess we can have a function here first. I guess we'll call this transform subject. The value to itself multiplied by the subject number. Start with the value 1. The value to the remainder. Can I do modulus equals? No, that doesn't make sense. So let's run this real quick. Seven and 8. See, transforming this subject, I get 0. We're supposed to start with 1. Five, 7, 6, 4, 8, and 1. Where does this initial subject number of 7 come from? Cryptographic handshake works like this. Card transform the subject number of 7 according to the card's secret loop. The door transforms the subject number of 7 according to the doors. All right, so what are we doing? We're getting encryption key. And to do this, we need card loop, door loop, Okay. Let's move this over here. I guess we already know the card public key in the car, the door pub. The card and door uses wireless RFID symbol to transmit the two public keys. Oh, the card transforms the subject number of the door as public key. I guess we can have this. The card transforms the subjects of the door public key. Door public key and card loop equals. Oh, that's weird. Card loop. No, door loop. Card pub and door loop. So we need to figure out I guess we can also have one here for guess we'll call this validate loop. We'll have the pub key and the loop. This will be what? Transform subject 7 and loop equals pub key. So I guess we could just loop through this, right? Start at 0, I'm going to say while validate loop. See if that finds us the proper loop. Loop of 8. So that was actually pretty fast. That's not too bad. Let's do the same thing for the public key. No, door loop. Door pub. And we would return transform subject. We just need to do one of these, right? Door pub and card loop. So in this example, the encryption key, it's not the encryption key we expected. Oh no, wait, yes it is. It's right down here. What encryption key is the handshake trying to establish? I mean, do we even need to do the door loop? I guess not. Alright, well, let's do the puzzle input. I feel like I have to put in more stuff here to get this working. Ooh. Yeah, this is significantly slower. I'm assuming because the key is going to be a whole lot bigger, or we're looking at a large prime. Because we have this number. Is this number a prime? You can use a compound assignment. Oh. Let's see, let's check this number. This is a prime number. And what about this guy? Are you a prime number? You're not. How about you? Neither are you. Well, I can see that it's an even number. What about these guys? Divisible by 7. And this guy? Oh, the same number. Now, what does that tell us? What are we on right now? Yeah, we got a pretty big card loop here. So we're multiplying we're starting with 7, which is prime number. We're multiplying by the loop. Multiplying by the subject. So we're always multiplying by 7 and then dividing by this result. What is this? You have a private and a public key. Let's see. E is your subject number. So what is this? Greatest common denominator. Yeah, I'm a little confused about this step. I mean, these aren't primes themselves. So we should be able to do this backwards somehow. Starting with the public key and then figuring out the loop. Inverse modulus? Which would be our public key and then something else. Let's get back to our example here. So this turned out to be a loop of card loop turned out to be 8, right? Big integer. Where is... Where's the big integer class in C#? Numerics. System.numerics. No. Big integer. There we go, mod pow. X to the power y modulo c. How would we... Inverse modulus. You know, we did this before with those, what was it? It was that Chinese remainder theorem. And in this case, it is, how do I figure this out? The modulo is a prime, which it is. That's annoying. Mod inverse. Oh, wait. Oh, that's somebody's private. If n is prime, so what would I be doing here? This doesn't make sense. Let's try a couple things. Hmm. What do we need to do here? Isn't it supposed to be like P times Q or something like that? Yeah, I don't know what I'm doing. I'm just taking shots in the dark here. Hmm. It's the greatest common divisor. Or is it supposed to be like -1? Hmm. Isn't it just... No. Let me see. So this guy... Hmm. Yeah, I don't know. I guess... Hmm. I want to get to the point where 7 going through a certain number of loops. It's supposed to be what is our E? Yeah, maybe I'm just not thinking about this properly. Let's see. Yeah, I'm not really sure what to do here. I think what you need to do is do an inverse modulus to figure out the loop, but exactly how that's applied to this multiply and whatever remainder problem we have here, I'm not exactly sure. Because we're basically saying what, like Um, I'm not sure what we're saying. We're saying 7 mod this equals this. Really not sure. No, this isn't right. Oh no, we need the remainder, right? Which is 8. No, that doesn't make sense. confused about the loop part of this. What does that mean? Why is it so much faster for this number? This is divisible by 7. Our puzzle inputs was divisible by 2. Card loop of 8. This one's divisible by 2. How long did this guy take? No time at all. Well, I mean, the loop is pretty small. Let's see, we need to consider this loop as pub key equals something times the number of iterations, the loop, plus something, some sort of remainder. And this is the same as what? Is B mod A? Eight isn't the remainder. The public key is the remainder, right? Oh, I never learned the math for these congruencies thing. Forget how you're supposed to properly represent them. But you basically, you have these congruency things. It can kind of help you reason about finding a certain iteration at a starting point. So our starting point is 1, right? We always start at 1, and we always have we're always multiplying by 7. Or no, we're always multiplying by the subject. Hmm. Now that this public key equals something times 8 plus something, right? So what would that be? No, I'm not sure if it works like that. Mm. Yeah, this is going to be a pretty boring one. I might even cut the stream out. It's going to be a lot of me figuring out how math works. Or maybe there's probably a super simple solution for this, similar to like that remainder problem that was done previously. These are always hard for me to reason through, though. So it'll probably take me a bit to figure out. What is this? 7. Hmm. This isn't working. Guess I can have this running while I'm goofing around with Wolfram. P and Q. Hmm. Extended Euclidean algorithm. Doesn't help. It's pretty much the same thing. I guess we can reason it now as, oh, this is where I kind of messed up. Yeah, this is, we can see it like this. The pub equals 7 to the power of x modulus this, right? How do we represent that properly? We would calculate it as an inverse modulus, right? Value exponent modulus, but we need the reverse. We need to solve for the exponent. I mean, is this any faster if we do it like this? What is this? 7 card loop. And then that number. Really? Why was that so fast? What? I'm not going to question it. All right. Oh. Here we go. We did it. Now, why that actually worked, I have no clue. Why is this so incredibly faster than this? I mean, it's sub-second, but it's still super fast. Is that not how you... I don't know what a reverse modulus even means. But I guess that's it. I mean, that's a pretty cheap way. I mean, I don't even need all this other stuff. Heck, you don't even need the second number. Yeah, look, there you go. Just a handful of lines is all you need. A modulus division. Is a modulus division different than what I did? The heck is a modulus division? I don't know. I googled how to do a reverse modulus and it gave me this. I'm not entirely sure what this means though. But I'm still looping through it. But I guess it just calculates it so much faster for some reason. Maybe there's some trick to it. Instead of, doing the normal way, which a computer does it, multiplying a number of times to get a exponent and then dividing by that number, taking the remainder. I would assume that whatever that is happening under this modulus division thing, it's figuring it out a lot faster. Yeah, I guess that's it. I mean, it took me a really long time. I'm still not entirely clear on what was going on. I mean, I came across this first and I did the brute force method and it was taking forever. So I assumed I needed to do some sort of inverse modulus calculation, but I didn't really understand how. Yeah, not a great rank for that last day. I guess it was a lot easier for other people. Or maybe everybody knew about modulus division. I'm not even sure why you would use that. Well, I guess to do these, what do you call them? These encryption processes. I haven't really done this in code. I mean, normally your public key is like a two coprimes, and you use those two coprimes to do something. Anyway, that's it for the advent of code. Oh, look at this. What's going on here? We've got a, is this our storm? And we got our moving sea monster. We found the check-in desk. We hacked our door. The soft serve machine broke. And a reindeer gave us the last coin. Oh, that's neat. That's our advent calendar. All right, that's it for this one.